Okay, then we continue with identification codes. So the next presentation is now on performant message identification from theory to practice. And Usman Ali will give the talk. So he is, in principle, I think your startups comes out from 6G Live somehow. So when we started to implement identification codes, then mainly Kaspar already started in Dresden with this, and also in our group we have Luis and Roberto doing some work, and it's really nice that you in your startup continue now and develop this codes. And I'm curious what you are telling us now. The stage is yours.
Thank you. Today in this talk, we'll start talking about like how can we take the results that we have in theory and then move to practice, right? Yes, so the content of the slides will be, first I'll introduce about what message identification codes are and how do we treat them like in practice when we go to the software development aspects of implementing them, and then talk about how some of the work that Casper has done on like some of the publications that they've made about different type of deterministic ID codes that we saw today and were explained in his presentation before, and how can we then optimize these codes so they can work with larger field sizes and exploit some of the new instruction sets like on ARM or x86 like Intel AMD based processors. And I will go also into the details of how we built our library that we plan to share in the future with other researchers to use and develop, to do some kind of like testing on real systems. And yeah, we'll show some results and some demo of the library. So in this talk, I'll focus mainly on the practical aspects of the development of the ID codes and look just on a general level, like how can we treat them as like some abstractions. So for implementation point of view, how do we look at these codes and how can we then use some of the library features in C++ or other programming languages, right? And also some features part of the CPU architectures to speed up the execution time for these codes so they can be more practical. I will not go into the theoretical definitions. I think those are pretty well explained in the previous talks today in the morning and also in the afternoon. And also not go into the details of the proofs of ID codes and hash functions, right? So to start, I will give like a simple example, right, of message identification, right, and compare it against the transmission scheme. And this figure, you've probably seen it a few times today. The idea is to treat like a message as some kind of a file, or it could be like some vector, right? And in a transmission scheme, you map this message into some code word and then send it over the channel, right? Like where it gets corrupted by the noise, and then you estimate the message. And when we draw the parallel with the identification codes, there we have these identities that gets, generated based on some message, right? Like, so you have some map of your whatever message you have to some identity, and then you take that, out of this probability distribution of this identity, and then you transmit over the channel where it might get corrupted, and then you land it somewhere in another probability distribution, and then you can decide, hey, if this was my message, and maybe it is, or it could be, some kind of error, or you can be sure that it's not your message if it's outside that probability distribution, right? So it's pretty straightforward. I think, I hope it's clear. Then these are some of the results, right? Like that we hope to achieve with this kind of code. So in the Shannon's transmission scheme, we get this like 2 to the power n times the rate, which hopefully achieves the capacity. And this is how much we can do with the traditional codes, right? The channel codes and the source coding algorithms, right? That we have in our current systems. And now with this, the random identification scheme, right? This is what hopefully we are planning to achieve, right? Like the double exponential gain in the number of messages that we can send, right? But we're now mainly focusing on the discrete identification. There's also something I now learned about the difference between these two, but it's kind of get somewhere in the practical sense where we are right now. We'll focus more on the discrete, case where we have already some set of messages that we want to transmit, and can we map them and then use them? The next slide here, I show like how it might look like in a integrations point of view, right? Like an ID code encoder could be part of some communication chain, and it will be done on the application level, right? So it will come before any other kind of like encoding scheme that's provided by the standards, like in Wi-Fi or 5G. And then you could either send it over some noiseless channels, or assume that the encoding works perfectly, and there's no corruption, and you can check it with some kind of CRC check that there's no change. So that also acts like a noiseless channel, right? And then you can verify in the end if this was the message that I was hoping to receive. And also, on the other hand, like we look into this case where it's a noisy channel, but then again, if we incorporate the ID codes inside before doing the regular transmission chain, then again we get some kind of source coding and some redundancy. So it's kind of a way to achieve noiseless case that we saw today presented by Casper. Yeah. So at the end, the verification is very simple, as I showed in the previous slides. Which is like a simple maybe that you're getting this identity or no. So this is something I'm not going to talk about, but mainly focus on the aspect of encoding, right? Because the receiver also needs to generate these, code words, right? And then just compare, my ID, is it matching or not? So at the end, there is kind of no decoder, just encoder, but at the transmitter side and the encoder at the receiver side with this additional step of verification for the identity, right? So that will be the focus of the talk today to make it efficient. As an example, I mean, you're probably familiar with the cryptographic hash functions. You might have used it to verify the SHA-SUM of a file, right, that you download over the internet, or maybe for your emails, or to verify security, as well as it's also used in Git in places. What it does is takes a message. This message could be of any arbitrary size or an arbitrary form, or it could be a file as well, like in any format. And we generate some kind of a unique ID from that file. And the goal in cryptography is to make sure that you cannot reverse back, to make it as good as the best cryptographic hash functions achieve this goal, right? So that it's not reversible. And this digest or hash that's generated, this could be of any arbitrary length, but for SHA-256, so of length 256, but there's also other SHA algorithms like 128 or 512. And the goal is to increase, if you increase the hash, right, it provides more more benefit to prevent some kind of false positive, or like some kind of errors, right? So the bigger the hash, the better, but of course it takes then longer to compute and might be slower. But with the newer generation of hash algorithms, they're pretty fast. And now if we go towards how can we, let's say assume we have this function and we want to convert it into ID code, right? So we have some message in the same way like with the SHA-256, but we also then now consider what the Galois field size is. So if it's the exponent like 2 to the power 32, then we get like 32-bit part of this code, right? So when I will present the results later today, they will be based on this concept, right? So if you have a bigger Galois field size of 2 to the power 64, then you take the first 64 bits, and then that will be your hash. And so keep in mind, like the speed to run this algorithm is independent of Galois field size you use, right? So you're just running the regular algorithm and then just computing the hash and then just considering the first few parts. Yeah. Then I'll also present some other ID codes that were published before, like Reed-Solomon ID codes and the Reed-Muller ID codes. And they also kind of work in a similar way. But there you take into this additional information, which is like the tag position. And here let's say, assume we hard-coded it to 5, but it could be then randomly selected, using some kind of common randomness or so on. But this will also generate some kind of a, unique ID. And this might look arbitrary bits, but they work in a similar way to the hash functions. And similarly, the Reed-Solomon concatenated codes work in the same way. You get some hash, but there you have like an outer code and then some inner code, which uses like half of the size of the, the outer code. Yeah, pretty straightforward. Then now we'll just present some basics, and then now we'll go more into the details of how can we optimize the implementation in the real world, right? So for Galois field, we have some fixed size like field set that's based on some prime powers of or the powers of some prime, right? Or it could be a prime, any prime number. So yeah, here's just some idea of how you could do like addition. And the main thing to take away from this is like it's a modulo addition, right? So you get some kind of a rep back, and you end up in the same set no matter what numbers you add from that set. And similarly with yeah, subtraction works the same way. And for multiplication and inverse, like in the case of like powers of prime, right? Like we have this generator polynomial, which is an alpha, right? So you take the powers, and then in the end, any power that exceeds the highest, size, it then ends up again in the same field. So this helps us to limit where we are, right? And also makes the computation a bit, yeah, straightforward to implement on any arbitrary CPU or general purpose computers, right? Because they also work in the binary fields. Yeah. When we think about multiplication, right, which is a big chunk of like what is used for polynomial-based hashing, or also for polynomial-based ID codes, like, or even the regular, yeah, Reed-Solomon codes, right? They all rely on these polynomials that are, the elements of that polynomial are the powers of, yeah, 2, right? And most of the general purpose processors, they have like a certain amount of space in their cache, which is quite small. And the goal for when you do multiplication based on some kind of lookup table based approach, right, is to ensure that you can fit that table where you would look up what the powers of the polynomial, maybe here I can show, yeah, like for example, 2 to the power 3, you want to make sure like you could map, the multiplication and the inverse of that multiplication, right, like back into that same table. And what we learned is that, for smaller field sizes, you could easily do it. It's like around 256 byte or, yeah, 128 kilobyte, and times 2 is, as I said, based on if it's the log and the anti-log table. And there's some latency that increases as we go, further away from the CPU towards, like the bigger caches. So we could do this up to 2 to the power 16, but then it becomes too difficult, and you might need around 16 gigabytes of memory just to put this in the yeah, to generate this table and then use it. So it becomes impractical. But for small sizes, it's more better to use a lookup table because it speeds up, the access time, and you don't have to do any computation additionally. Yeah. So keep in mind this like latency constraints, and this is why we developed this library to then handle the case for higher field sizes. So beyond 2 to the power 16, then you need to exploit some other ways to do multiplication. Yeah. And that's what the talk is about today. Here is an example again. This is from Intel. Like they provide like some of the reference guidance for AES encryption or careless multiplication, right? I hope I can move it away. Okay, this is better. So here you can see they have like an example of how you can multiply numbers that are 64-bit or more. And this exploits some of the instructions that are available in the CPU. And we'll kind of use this to our advantage, right, to work for higher field sizes and show how we yeah, made this like realizable. The instruction that we specifically use is this PCL QDQ instruction, right? And we found a similar instruction also for other platforms, but in the case of Intel or AMD based systems, right, any processor that's beyond 2010 onwards, right, like the modern ones that you found in your laptop or servers, they support this, and even your smartphones have this support speed of multiplication of 64-bit numbers, and they have this 128-bit registers as described here. And this gets not only used for for ID codes, but it's already being used for AES encryption and yeah, other kind of CRC checks and so on that requires these large numbers to be multiplied together. Yeah. So here I would like to briefly mention like the ARM architecture, which also since I think a few years ago onwards, like it supports yeah, since ARM v8 version onwards, right? That's found in like the modern like Raspberry Pi, or it could be your laptop, like the recent laptops announced by Snapdragon X Elite, which are also based on ARM v8 and onwards, they have these crypto instructions, and this is similar to the instruction set that's found in the Intel side, right? To support SIMD instruction as well as 64-bit multiplication and so on. So this is part of might be familiar with the Neon instruction set. So yeah, it's good that we can now implement this on from a wide range of processors, from the small to the Raspberry Pis to the smartphones to servers or laptops. Yeah. Here's just an example of what these instruction registers look like. Yeah, so these general purpose registers are limited, so you have to be careful, like other applications are not using it the time when you are trying to do something. And yeah, just use these registers to then store the results of like 64-bit multiplication. So it will be then used in 128-bit registers, and this is then found on in both Intel x86 as well as AMD. Yeah. To learn more about this, PCL-MEL QDQ for x86, and as well as like this ARM PMEL or PMEL2 instruction set, which is based on the Neon architecture that I mentioned, can look at this blog post where you go in really into the depth of how these low-level like assembly instructions work. Yeah, but essentially it's some kind of like bit shifting one at a time and XORing the results. And this is also described pretty well here. In this slide here at the bottom, you can see we get this, like a for loop where we are doing this, XORing, and then we are doing a bit shift, and then, multiplying two numbers like X and Y, and then you just get the final result out. So it's quite straightforward to use. Okay. Now we'll talk a bit about, for our library, what kind of templates and C++ implementation we use to speed up the computation time. Our goal was to then simplify this interface from smaller field sizes to the large ones. And we do this by dynamically shifting the data type, from like unsigned int 8 type to unsigned int 64-bit. It's automatically selected based on what field size you're working with. And we tried not to use any kind of other special acceleration or some kind of compilation steps. So it's something that's already available on the hardware, and you're always allowed to like use it, right? So there's nothing special going on. We tried to compile for the best native architecture. So if we build like a general build, it might be a bit slower, but when we did our benchmarks, we did it for that specific CPU type. And for example, for ARM, we included in this ARM v8 plus crypto instruction set to enable it. The idea was to reduce the memory usage by using this kind of templates and speed up this computation in the end. And in the end, you could generally build like the library that could be installed on any system, but it might be a bit slower, but it will definitely be compatible, and you don't have to build it from the source every time. One last point, which is very crucial that we mentioned, is when you're multiplying two numbers, there might be like one of the operands might be 0, or sometimes in your multiplying they might encounter zeros. So you could add this check that if there's a 0, then you don't have to even do a multiplication. You could completely like speed up the process if you have to do repeatedly multiply, for example, in Reed-Solomon codes and so on. And now some benchmark results. These are what we're able to achieve. First, I will show two results. The first one is for ARM 64, and we did this test on this Qualcomm Snapdragon X processor, the latest Ubuntu versions. Here you will notice like I've shown the mean time that as it scales for increasing message size, which is presented in kilobytes, and the time is in microseconds. And you can see the lower the time is, the better. In the Reed-Muller codes that we implemented with the highest field sizes, they achieved the best results. But for small field sizes, they're also comparably fast. And then on the second best is like the SHA algorithm, right? And the SHA-1 is kind of like overlapping with the Reed-Solomon codes and the concatenated Reed-Solomon codes, which are also like pretty fast if they are comparable to the SHA algorithms, which is also quite commonly used for hashes. So I mean, this is the one that we were able to achieve with our current implementation, but we could improve it more. And the throughput on the other side is, just the inverse of this, graph, which showing in gigabits per second. And you can see quite high throughput you can achieve if you're using ID codes. Yeah, and it's scaling initially for smaller, sizes. You might have noticed that, they kind of converge to the same time, or the throughput is a bit low if you're working with smaller messages, but for larger messages, throughput is high, but then it stays constant, even if you increase the message size further. And on the next slide, I show similar results on x86 or AMD. And here also you can notice the speed is similar to the one that we achieved on ARM. And yeah, it's also quite fast, maybe a little bit even faster than on ARM. Yeah. And with that, I will show an example, right, of how we did this like benchmarking and this timing, right? This is just a simple C++ code, and you can ignore most of it, but if you focus on the highlighted part, it's just provide a message to the API and the position where we want to compute, and this position then could be randomly selected, or it could be something that's predefined. And then we compute the method on the exponential array and the log array, right? That I mentioned, the log and anti-log table. Depending on the field size, if it's less than 16, then we use these pre-computed tables. And otherwise, we then rely on the bigger sizes. So we don't pre-compute this beforehand. And then we measure this time in some nanoseconds and print it to the console. And if you were to use our library, you just have to define what kind of encoder do you want, what field size are you working with, and the position. And this position could, again, be randomly selected. And that's all you have to configure to work with it. The main program would just simply look like this. You have, some data type, this template type that I mentioned for C++ that you select. And you call your generate the object, and then simply pass it on to the function you're working with. And for files, we also made it dynamic so that depending on the field size, you read the files into the right data type. Like for example, GF 2 to the power 8, then we'll then store it in unsigned int 8 type. And for 2 to the power 64, we use it 64-bit unsigned int types to store the data. And and then you could generalize the library API to other methods as well, like SHA-1, SHA-256, as well as RS2 and RMID, and call your function, and it's just the one line in the end. So our goal is, to build and demonstrate like this library and share it in the future with, with the researchers. So we're currently working on the second release, and plan to share like dynamically linked libraries. So you could just install it on your Ubuntu or like your Linux environment, and you could just call it inside your applications, or you could use the built-in command line interface to use it. And then for Windows, we plan to share like an executable you can work with, and we have some additional methods for files and so on. So you don't have to, you can abstract that problem as away, and some scripts to benchmark and to also build examples that we plan to provide. This is like one simple example with the CLI tool that I showed, right? Like earlier, the code. And this is what you might see, like you might pass in like this beyond the bound paper as a PDF. It's around 6 megabytes. And then you can see the time that it took for each of the algorithms in nanoseconds. Which is pretty fast. And you can also see the output, right, that you would expect as a tag or the hash. That we then abstracted away. And this is shown in the right data type that we use. For example, for 64-bit, then it's, unsigned in 64 number. I want to mention about like what did we use for implementing them, right? So for SHA-1, SHA-256, and so on, you can already use standard C++ implementation from OpenSSL, and these are already quite fast enough that you don't need to re-implement them yourself, and they've already been optimized. And there are other SHA algorithms that are even faster than not just SHA, but other hash algorithms that are faster than SHA-256, and you might plan to also use it and then make it part of our library. For read Solomon and so on, we optimize these codes for like high performance throughput, and we demonstrated like the best results that we have. We were able to achieve on different platforms as well. And for the research articles, where you might find the definition of the algorithm and so on, you can look at this repository, which is open source and publicly available. And final remarks. So what we have is this like library plan to share, and the idea now is we have achieved this like fast speed and high throughput, and we can now just simply use this library as part of like deterministic ID codes without the need for a decoder, and yeah, make some applications out of it wherever these are used. We also have some, collision like probabilities and benchmarks that I didn't show today, but yeah, those are also like in proven theory, and also you can use our library to do this kind of testing with like a brute force way to check how much collisions do you obtain. And yeah, so that should be it. And I will finish with some future work that we're planning to do. So Linux first approach allows us to then easily incorporate in your existing stack, which is quite common, like open air interface. In the future, we plan to then use this library to then test real world gains and transmission, and therefore like see how much energy could we save by using ID codes. So this was one of the main motivations to look into identification codes, is you don't have to transmit more data, just send an ID. But we also want to then look at how much computation it takes, how much energy it takes to compute the encoding process of ID codes. And also incorporate into existing stacks like in 5G and so on. And we like to develop like some applications like with SDRs, and there we'll also like demonstrate some aspects of common randomness and so on. And also plan to add Python binding, so you can incorporate into existing open source tools that use Python and do some simulations work. I would like to finish it with this question, like how can we help you with this library? Thank you.
Your library, do you use hardware accelerators you has mentioned? Like it means that there is some restrictions or requirement on the hardware, right, for the library, right?
So what I think I mentioned here, let me go back, is yes. So we use this careless multiplication instruction that's found on most of the ARM and as well as like x86 processors in circa 2010 onwards. So it's not something special like an FPGA or something, but we are using something that's mostly present on the processor. Any 64-bit processor these days, like from your smartphones to micro. I don't know about microcontrollers, but maybe general like purpose CPUs have it.
Not, right? Okay, but for the CPUs.
Yes, so it's a software-based approach. So
you do need a stronger.
Like it's not that strong, I would say. Any 64-bit processor that you have, maybe it will not work with, as I mentioned here. So anything that's below ARMv7 onwards, like Raspberry Pi 3 or their 32-bit processors, they don't have this instruction.
Included or not included? I think you need at least ARM8, right?
Yes. Yeah.
Okay.
That's the idea.
Another question is later the benchmark you have shown this amazing result. You use this edit code, the RM read more edit code, and with the hash. Okay, so this is the field you are not this one. Actually, the timing. I think you have this timing to do like to calculate the digest the tag of this file. Yeah.
Yes.
I was a little bit surprised by how fast you do that. My question is that, of course, being fast is good, but I think before people choose which one to go, the thing is that again the security level. So security level for SHA, for example, 1 or 256. So there's like it's more clearly defined. So people know, okay, the collision rate is this level.
Yeah.
But for the read-molar, so if the comparison should be done, like it's expected they are at a similar security level, then you do the comparison on the timing. So if you guarantee kind of similar security level, you know, based on this collision rate, then your timing is even better. Of course, this is the best.
Yeah.
So I actually does this part because for SHA, it's clear, but for the read-molar ID code, it's not clear the security level.
I think I think as you mentioned, because it's so many codes that are based on the block codes, right? So we have this maximum distance, you know, between the different code words, and that's the kind of thing that we're trying to exploit when we developing ID code. No, not like Reed-Solomon codes, I mean. Yeah, that's what I mean. The idea is, yeah.
But here you are
just those.
using read-miller code.
That was an example, right?
Yeah.
But I mean, yes, you could also look at the results for Reed-Solomon. Yeah, those are also quite fast and comparable to, yeah, the SHA-1. They're a little bit, yeah, they're kind of overlapping. But yeah, if you want to use read-miller, it's a bit faster. But in practical applications, it might not be that important. But maybe you can, Casper. Yeah.
Of course, SHA is a cryptographically secure
Secure.
hash, and neither Reed-Miller nor Reed-Solomon is a cryptographic hash. So at least it's not proven yet, and I don't think it can be cryptographically secure because the ID problem is about accidental collisions due to the hashing, right? And it's not about protecting against purposefully constructed collisions, which is what you would need if you want to protect against cryptographic attacks. So it's a different kind of problem, and to create a cryptographic hash code, maybe based on linear block codes or whatever, is an additional problem. Or if you want, maybe you don't even have to do this, because if the randomness that you use is secret, because either it's some kind of common randomness generation that no one else can access except for the two parties, or you just have a pseudo random number generator and you have a secret key that is started at the beginning, and then you just exchange the tag position, right? So the digest, but no one really knows which hash function, so which part of the Reed-Solomon code word you actually used. And then it's also not, then it's also secure because I mean, maybe you could reverse the function, but the attacker does not know which function out of billions of functions was used. So, and then you are also secure if the randomness is not detectable or interceptable by anyone.
Yes, maybe the comparison is not fair anyway. So not comparable. Anyway, this with hash functions. Another one I think of with hash functions, you could have any the input of the length, right? You don't have any restrictions. I think for the ID code, basically you have restrictions on the input length. Yeah.
So the comparison is, I would say, it's fair up to a certain point, because in this case we're using the hashes, the SHA hashes, not as they were originally intended to. So a little bit of history how we started. We wanted to implement the concatenated Reed-Solomon codes to do ID codes because they are capacity achieving. But to implement concatenated Reed-Solomon codes was very slow on hardware. And then we said, okay, let's not use a capacity achieving code. Let's use a bad ID code that is very fast, and a SHA with hardware acceleration was very, very fast, and it was really, really fast. And that's what we did. And that's why we started with the hashes as a baseline. But then it turns out that if you look deeply into how Reed-Miller operations are done or Reed-Solomon operations are done, and then you look further into how you can accelerate this with the hardware that you have available, it turns out that Reed-Miller and Reed-Solomon can be implemented more or less with comparable speeds as these hardware accelerated SHA functions, which means that you can have ID codes that are capacity achieving and the same performance in terms of speed as that you would generate using a bad ID code with a hardware accelerated by using a SHA as a technique. So this is the reason why they are there, right? So it's not there because of their cryptographic nature. They are there because it's something that every hardware or many CPUs are accelerated to compute really, really fast.
I think I can also add this master thesis, what we have there we tested several, also not also cryptographic hash functions, also other hash functions. We all tested them for performance. So that's also somehow how we come to that. So that was a different goal. Somehow our goal was always look at the performance of the ID code and of the finite performance. That was the main idea of us.
I think it's good because I mean, if you are considered just let's say the complexity or the timing, actually it's good because SHA or the AES is widely used, and people kind of they accept it. So they have like a tolerance. So within this timing, it's okay, acceptable. So we can consider it for the application if it's a really a nice one. So yeah.
Just as one final comment, I think it's maybe not important whether, I don't know, maybe SHA-256 runs at 3 gigabits per second and Solomon runs at 2 gigabits or 4 gigabits. I don't think this is really important because then, as Usman already said, it really depends on the platform you run it, and maybe you don't want to run 64 bits but only 32 bits or something, then it varies. The main point is that it's not slow to use concatenated read Solomons anymore, and read Muller is even much faster. So
Yeah.
it's this this roadblock of having very slow encoding speeds is not there anymore, and so these kind of codes can be used, or we can look at other problems that might come, right? So this was the point, not to say this is now better than SHA, because it's a different code and it's intended for a different purpose.
So I was just imagine, so the read mirror code, because I mean, you have the ways to optimize the performance.
Yeah.
Does it, is it because that you are working on the extended field, or is this binary field or extended of this field of it? Instead of, because with mirror code, you work in the prime field and its extended field.
Yeah.
Is this the reason that the calculation in the binary field and its extended field, it's kind of, you can speed up?
What generally I can say for computers, right? They prefer binary stuff or powers of 2 to store data. So yeah, everything can fit in memory and also in the caches. So there it accelerates not just read Muller, but all the codes benefit if you choose your parameters that are powers of 2.
All the question is like your implementation. So the read Muller code, it's always 2 to the power.
Yes.
But the read Solomon code,
It's also yes.
it's also 2 to the power.
Everything is that's
Okay.
why these are the exponential size is the power of 2.
Okay, good to know.
So
Thanks.
that's why.
Then thank you again.